Solving a system of two equations by substitution. Well, this is different than elimination. The strategy involved is to choose one of the equations, solve that equation for a variable. In this case, we've got x's and y, so it could either be x or y, and then substitute what you get when you solve that equation for that variable into the other equation. For example, what I'm going to do is I'm going to solve that equation, the second one down, for x. So here's what I'm going to do. X plus y equals 7. So I end up with x equals minus y plus 7. So I'm going to take that result and I'm going to substitute minus y plus 7 in for x in the other equation, like this. Here we go. Instead of writing x, I'm going to write minus y plus 7. I'm going to put that in brackets just to be clear what I'm doing. So instead of x, I'm writing negative y plus 7, just putting in brackets clear. And now I'm going to go minus y equals minus 1. Well, now I'm going to collect terms. Well, I have two negative y's. That means I've got minus 2y plus 7 equals negative 1. Well, I'm going to isolate the variable y, so I'm going to subtract 7 from both sides. And what I end up with is negative 2y equals negative 8. I divide both sides by negative 2. Anything divided by itself is a 1. So y equals, well, negative 8 divided by negative 4. A negative divided by a negative is a positive. So that means y equals 4. Okay, so now what I'm going to do, I'm going to take this value, y equals 4, and I can put it into any of the two equations that I started with. So I might as well use the first equation. X plus y equals 7. I discovered that y equals 4. So I'm going to substitute a value of 4 in for y. So I'm going to have x plus 4 equals 7. So now I add negative 4 to both sides. I end up with x equals 3. So the solution of these two equations, the system of equations, is the point x equals 3, y equals 4. Now, there are special cases involving systems of equations, and these cases are sometimes you have no solution with a system of equations. Sometimes the solution is, well, all real numbers, like any number will make a system of equations true. And sometimes you have a solution. So let's just take a look at a couple of special cases. So with example 3, got two equations. 3x plus 2y equals 6. 3x plus 2y equals 5. What I'm going to do is I'm going to put these equations in slope-intercept form, y-intercept form. What that means is the equations are going to be like in the form of y equals mx plus b, where m is the slope and b is the y-intercept. Notice that with these equations, the coefficients in front of the x's are the same, the coefficients in front of the y's are the same. The constant values are different. Okay, so let's just proceed here. We'll call it equation 1, and that will be equation 2. So I'm going to solve equation 1 for y. So here's equation 1. Solving for y, I have to isolate y. So I'm going to add the additive inverse of 3x to both sides, which is minus 3x. That gives me 2y equals minus 3x plus 6. Well, I'm going to divide both sides of this equation by 2. Now anything divided by itself is 1, so the 2's cancel. And I end up with y equals minus 3x over 2 plus 6 divided by 2, which is 3. All right, now I'm going to solve equation number 2. Here we go, equation number 2. Equation number 2 is 3x plus 2y equals 5. I'm going to add the additive inverse of 3x to both sides again. So negative 3x gets added to both sides. Now I have 2y equals minus 3x plus 5. Well, where am I at now? Well, I'm going to divide both sides by 2. Once again, the 2's cancel. So y equals minus 3x over 2 plus 5 halves. Well, what do you notice about these two equations? Well, here's equation number 1, and the slope of equation number 1 is negative 3 halves. The slope of equation number 2 is negative 3 halves. These lines have the same slope, so they are parallel to each other. These equations actually have no solution. The system of equations has no solution. So I'm going to graph this system, and we'll take a look at that. So I've got two equations. Y is equal to negative 3x over 2 plus 3. Y is equal to negative 3x over 2 plus 5 halves. I'm going to plot the graphs of these two equations and graphically find the intersection point and compare that to the intersection point I've calculated, if there is one. According to my calculations, the slopes are the same, so there should actually be no intersection point. So there should be no solution. Let's just see what happens. So I've made up two data tables for x and y values. Table number 1 refers to the equation negative 3x over 2 plus 3. Table number 2 is referencing y is equal to negative 3x over 2 plus 5 halves. I'm going to plot the data now. First of all, I'll plot the data for number 1. And here we go. So 0 and 3. So I plotted the data for equation number 1, and now I'm going to draw the best straight line through those points. Next, I'll plot the data for equation number 2. So now I've plotted the data for graph number 2. and I'm going to draw the best straight line through those points. Notice that these lines are parallel, and as a result, the equation has no solution because I've graphed a line for each equation. Both lines have the same slope. They have different y-intercepts. Equation number 1 has a y-intercept when x equals 0, y is equal to 3. Equation number 2 has a y-intercept of 5/2 when x equals 0. What you should do when you are drawing graphs is always write the equations down on the graph, just so it's clear which equation represents which graph. So here, I'm going to go that equation in red is y is equal to minus 3x over 2 plus 3. The other equation, equation number 2, is y is equal to minus 3x over 2 plus 5/2. If you want, you can circle things so it's clear which equation belongs to which graph. Okay, 2 more equations. Let's just see what sort of graphs we get out of these 2. So I'm going to label these equation number 1 and equation number 2. So for equation number 1, what I'm going to do is solve it for y. So here's equation number 1. Solving for y. Or in other words, y equals 2x minus 4. That is equation number 1 solved for y. So now equation number 2, separate them. X equals y divided by 2 plus 1/2, or plus 2. Y divided by 2 plus 2. Oh, that's not right. Solving this equation for y. Well, the first thing you're going to do, you notice here I've got y divided by 2. So I've got a fraction. So I'm going to multiply everything by 2. Here we go. So I'm going to end up with 2 times x equals 2 times y over 2 plus 2, which results in 2x equals 2 times y over 2 is y plus 4. Solving for y, I end up with 2x minus 4 equals y, or in other words, for equation number 2, y equals 2x minus 4. So what do I notice about this? Well, for both 1 and 2, the slope equals 2. The y-intercept, the value of y when x equals 0, is equal to minus 4. My prediction is that both of the graph of each of these 2 equations will overlap. Let's just see if that's true. both equations 1 and 2 have, well, they're the same. Y equals 2x minus 4. So they must be overlapping each other. Let me just graph this. Make a table of x and y values. When x is 0, y is minus 4. When x is 2, 2 times 2 is 0. Oh, sorry, 2 times 2 is 4. Plus negative 4 is 0. When x is minus 2, 2 times minus 2 is minus 4. Plus minus 4 is minus 8. Plot the points. When x is 0, y is minus 4. 1, 2, 3, 4. When x is 2, y is 0. And when x is minus 2, y is minus 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now I'm going to connect the dots and make a straight line graph. Like this. Put arrowheads on it. And this is a special case where we had two equations and two unknowns and the overlap. So this is the graph of y equals 2x minus 4. So the two equations we were working with, equations 1 and 2, actually when they solved for y gave the same thing. So this is a special case. You have two equations and two unknowns, and the graphs overlap each other. So the solution here is all real numbers. Any value of x makes both equations true. Now, let's look at this situation. Y plus 2x equals 10. 2x minus y equals 6. I'm going to label y plus 2x equals 10 equation number 1. 2x minus y equals 6 equation number 2. And I'll solve equation number 1 for y first. So here's equation number 1. Solving for y. So equation number 1, solve for y, is equal to minus 2x plus 10. Now I'm going to solve equation number 2. Equation number 2 is 2x minus y equals 6. Solving for y. Now I've got to isolate the y. So I've got a y plus 6 on the right. I'm going to add negative 6 to both sides. I end up with 2x minus 6 equals y, or in other words, y equals 2x minus 6. Okay, that's equation number 2. So equation number 1 is that. Equation number 2 is this. Well, what do we know about these? Well, equation number 1, if you look closely, the value of the slope is minus 2. In equation number 2, the value of the slope is plus 2. Okay, well, let's see if these equations intersect. Notice they both have different y-intercepts as well. So I'm going to graph these two equations on the same set of axes. All right, to begin with, I'm going to create a table of x and y values. Ordinate pairs for equation number 1, y equals minus 2x plus 10. 10 there. So when x equals 0, y equals 10. When x equals, 2, minus 2 times 2 is minus 4. Minus 4 plus 10 is 6. When x is minus 2 times minus 2 is plus 4. 4 plus 10 is 14. Okay. For equation number 2, might as well calculate the ordinate pairs when x equals 0. Anything times 0 is 0, so y then is equal to minus 6. When x equals 2, well, 2 times 2 is 4. 4 plus minus 6 is minus 2. When x is minus 2, 2 times minus 2 is minus 4. Minus 4 plus minus 6 is minus 10. All right, well, I'm going to plot the data on my set of axes. Now, you notice how for equation number 1, the values go up to plus 14. For equation number 2, they go down to minus 10. My axes, I'd have to use a lot more paper to deal with this. What I'm going to do is I'm actually going to alter my scale a little bit and say that each division is worth 2. And I'm going to indicate on here. I'm going to say that's a 2, and that's a 2. This would be indicating that both axes are going up in units of 2 now, so each major division is a 2. So I'm going to plot the points. So for graph number 1, when x is 0, y is 10. So that means I go up 5 squares. 1, 2, 3, 4, 5. So that's the point 0, 10. Why don't I just label that? That really makes it clear that we're going up in units of 2. The other points come over 2 and I go up 6, 3, and I go to the left 2, and up 14, which is 7 squares. 1, 2, 3, 4, 5, 6, 7. Okay, and now I draw my best straight line through there. As I said, I draw my best straight line through there. Here we go. And that's the graph of equation 1. And now for the graph of equation 2. When x is 0, y is minus 6, which means I come down 3. There's a point there. When x is 2, y is minus 2. So when x is 2, y is minus 2. Oh, I got a point there then. And when x is minus 2, y is minus 10. So come to the left 1 square and down 5. 1, 2. Okay. And so now I'm going to draw my line of best fit. So interesting. There we go. So I've got an intersection point there. So these two graphs actually have a solution. Graphically, what does the solution look like? Well, the graph, remember going up in units of 2, it looks like that the solution of this equation have gone to the right 2 squares, so that's 4 for the x value, and I've gone up 1 square, so that's 2 for the y value. I'm going to solve these two equations and see what I get. Well, what do I know? Well, I know that I've got an equation. Number 1, y equals minus 2x plus 10. And I have equation 2, y equals 2x minus 6. Well, what I'm going to do, I could have used the original equations and either used the method of substitution or elimination to find a value for x, but I've solved actually both of these equations for y. So if I actually want to find the solution, both equation number 1 and equation number 2 are equal to y. So I can actually set both of these equations equal to each other. So since y equals minus 2x plus 10 and y equals 2x minus 6, I'm going to say minus 2x plus 10, that's equation number 1, equals 2x minus 6. Okay, I'm going to solve this for x. Let's see what we get. So, yeah, I'm going to add negative 2x to the right-hand side. I'm going to add negative 2x to the left side. So now I've got minus 4x plus 10 equals minus 6. Well, I have to isolate the term with the variable in it. So I'm going to do that by subtracting 10 from both sides. All right, well, what do I have now? So I'm going to have minus 4x equals minus, well, negative 6 plus negative 10 is negative 16. Well, I got to solve for x. I got to isolate for x. So I'm going to divide both sides of this equation by minus 4. That's the number that appears in front of the x. Well, anything divided by itself is 1. So minus 4 divided by minus 4 is 1. So what I'm left with is x equals negative 16 divided by negative 4. Well, negative divided by negative is a positive, so x equals 4. Okay, so I've got the x coordinate of my solution. Now what I'm going to do is kind of calculate the y coordinate. I could use either equation 1, or I could use equation 2 to find my value for y. I'll use equation 1. So if we have y equals minus 2x plus 10, well, x is equal to 4. So that means that y minus 2 times 4 plus 10. So y equals minus 2 times 4 is minus 8 plus 10. So y equals 2. Well, that means we have a solution set of 4, 2, which is what we saw from the graph. But as I said, I could either use equation 1 or equation 2. Well, let me just prove it to you here. So I'm going to have equation 2 now. I'm going to go, well, y equals x minus 6. Well, I said, okay, well, x is equal to 4. So that means that y equals 2 times 4 minus 6. Well, 2 times 4 is 8. 8 minus 6. So y equals 2. Once again, I get the same value for y, proving that I could use either of the two equations. So my solution is 4, 2. 4, 2 is where the two graphs intersect, as seen here in that picture. So the solution of the system of equations involving equation 1 and equation 2 is the point 4, 2, where the x value is 4, the y value is 2. That's it.